Welcome back, everyone, to this lecture on supervised learning. Supervised learning algorithms are trained using labeled examples, and that's a key word, label, such as an input where the desired output is known. That means within your data set, you're going to have some historical features with historical labels. So you already have that information, such as a segment of text could have a category label. So you take a bunch of previous emails and someone has already gone by and classified them using the correct label. So they read the email and classified it as spam versus legitimate. Or we have a bunch of movie reviews and someone has already gone and labeled movie reviews either positive to the movie or negative to the movie. And then the idea would be for future text information, such as a future email, using that historical label data, the network or machine learning algorithm could learn off the historical data in order to predict for new data whether it belongs in the spam category or legitimate category, or in the positive category or negative category for these movie reviews. So the way this works is, for neural networks, the network is going to receive a set of input data along with the corresponding correct outputs. And then the algorithm or network will learn by comparing its actual output with correct outputs to find errors. And then it will modify the model accordingly, such as adjusting the weights and bias values in the network. And don't worry about those two key terms. We'll discuss those in a lot more detail when we talk about neural network theory. So supervised learning is used in applications where historical data predicts likely future events. And the machine learning process for supervised learning looks like this. So let's go ahead and go through this step by step. So the first thing we need to do is actually get data. And it depends on what domain you're working in where this data actually comes from. This can come from your customers, or it can come from collecting things into a database online, or maybe it's physical data and it comes from sensors, etc. So at some point, the data has to actually be acquired. Once we actually acquire the data, then we need to clean and format the data so that our neural network can actually process it. And often we'll do this using a library called pandas. Then we split the data into training data and test data. And we'll talk about this particular step in a little more detail towards the end of this lecture. But what we do here is we take some portion of our data, maybe like 30% to be test data, and then the larger majority of the data, like 70%, to be our training data. And what we're going to do here is we're going to use that specific training set on our network or model in order to fit a model to that training data. Then we want to know how well our model actually performed. So we then run that test data through the model and compare the model's prediction to the actual correct label that the test data had. Because remember, we actually know the correct label for that test data. So you can run that test data features through the model, get our model's predictions, and compare it to the right answer. And then we can evaluate the model, and then maybe we want to go back based off that performance and adjust the model parameters, maybe add more layers or more neurons to try to get a better fit onto that test data. And once we're satisfied with this, we can then deploy the model to the real world. Now, something to note here is what we just showed was technically a simplified approach to supervised learning, and it does contain a key issue, which we kind of touched upon during that test train split. And the question arises, is it fair to use that single split of the data into one test set and one training set to actually evaluate your model's performance? So when you actually test your model on the test data, you'll get some sort of performance metric. For regression tasks, it could be something like a root mean squared error. For a classification task, it could be something like the accuracy. But is it actually fair to use the accuracy you get off that test data as your model's final performance metric, since technically, after all, you were given the chance to update the model parameters again and again after evaluating your results on that test set? So how do we fix this conundrum? Well, to fix this issue, the data, especially in neural networks and deep learning, it's often split actually into three sets. And we have training data, validation data, and then test data. So we kind of introduce this in-between step of this validation. And so what we end up doing is we have these three sets, and we have the training data just as we did before. And this is used to train the model parameters. So the model gets to look at the features, look at the correct output, and then fit to this training data. And then The next step is our validation data, which was kind of our test data from before. And so what we do with this validation data is after training on the training data, we check the performance on the validation data. And maybe based off that performance, we go back and adjust our models, maybe adding more neurons or adding more layers, changing the actual architecture of the network, etc. And then you kind of repeat that process over and over again until you're satisfied with your model's performance on the validation data. And now it comes time to evaluate the true performance of your model. So what do? Well, that's why we have that third split of test data that the model has never seen before. And what you use that final test data set is to actually get some final performance metric. Now the key thing to note here is that once you run the model through the test data, that's going to be the performance metric that you expect your model to actually perform with in the real world, since you're not going to go back and adjust your model's weights or parameters or anything else. Once you actually go onto that final test data set, you're technically not allowed to go back and adjust the model in order to try to refine your performance on that final test data set. So you can think of it this way. You train on the training data to actually fit your model, then you use the validation data to see how your model performs on unseen data, and then go back and adjust your hyperparameters. But when it comes time to actually kind of report to your boss how well will this model do in the real world, that's where your final test data set comes into play. And the test data set, once you actually pass it through the test data and you get that performance metric, that's it. You don't really get to go back and adjust the hyperparameters. Otherwise, you're kind of cheating yourself again on understanding the model's real performance on truly unseen data. So what this means is after we see that result on the final test set, we don't get to go back and adjust any of those model parameters. This final measure is what we label the true performance of the model to be on unseen data. Now, in this course, in general, we're going to simplify our data by just doing that single train test split. While technically we could be doing another split to get both a validation and a test set, for the kind of problems and exercises we're doing in this course, since we're not really deploying a lot of these models to the real world, it's not a huge deal that we essentially just have a training set and a test set, and we skip the sort of like in-between validation set. So we will simply train and then evaluate on a test set, and we'll leave the option to the students to go back and adjust the hyperparameters. And then after going through this entire course, you're going to be able to easily perform another split to get 3 data sets if you desire. So you'll be able to easily create a training set, a test set, and a validation set if that's what you want. But just want to tell you, in this course, we'll keep things simple and just train on a training set and then evaluate on a test set. And we won't really go back and adjust hyperparameters. We'll kind of treat that test as the final. And again, you can always go back and add in more neurons or more layers or more hyperparameters to your network. That'll be really easy to do. And we'll kind of leave that up to you as a student to decide if you want to continue with that. Okay, let's go ahead and move on to discuss things like overfitting. I'll see you at the next lecture.